Hi Wildcats, this is Unit 9 Focus Question 3 example problems. So we're going to be looking at the conservation of energy, mechanical energy, work, the transfer of kinetic and potential energy back and forth. So in our first problem here we have a student and their cell phone is at rest on their lab table, 0.74 meters above the floor. It says if the student's phone has a mass of 0.112 kilograms, what is its velocity when it hits the floor? So assuming this gets bumped off and then falls to 0.74, when it gets to the bottom, what will its velocity be? So some things that we know that since it's at rest, its initial velocity on the table is 0. And when we look at this, we know however much energy it has here. Right? At the very top, all of its energy is going to be potential. And at the very bottom, right before it hits the floor, when its height is 0, all of its energy is going to be kinetic. So however much energy it has here, the total energy or mechanical energy it has here, it has to have the same mechanical energy here when it hits the floor. So we can say the mechanical energy initial is equal to the mechanical energy final. Or long form, kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. So as we know, it says V initial is 0. Well, if its initial velocity is 0, then it's got no kinetic energy at the top. Right, 1/2 mv squared, this is just going to be 0. At the bottom, it's got no height, right? Its height would be 0. And so since there's no height and potential energy final is mass times acceleration due to gravity times height, height would be 0, so there would be no potential energy at the end. So then really this just comes down to calculating the initial potential energy and then using that to find velocity, because potential energy initial is mass times acceleration due to gravity times height. That's going to be equal to the kinetic energy final, which is 1/2 mass velocity final squared. And so if I do some algebra, if I multiply both sides by 2, that's going to get rid of my 1/2. And now I divide both sides by m. Interestingly, mass doesn't actually matter, right? Because it's the same. So it's going to cancel out on both sides. And then this is velocity final squared. So I need to take the square root of both sides. And I would be able to figure out velocity final by taking 2 times the acceleration due to gravity times height and then square rooting the whole thing. So that's going to be the square root of 2 times 9.81 meters per second squared times the height, which is 0.74 meters. So something a student might ask me in class here is, but I thought this needs to be negative. Acceleration is a vector, it has direction. That's true. So then if we made this negative 9.81 meters per second squared, we would also need to treat this as a negative because it will have gone down 0.74 meters. So I could put in negative 9.81 and then I'd need to put this in as a negative. Well, negative 0.74 times negative 9.81 is still going to be a positive value. So velocity final is equal to, if you put that all in your calculator, I get it to be 3.81 meters per second. Now we also could have gotten that with kinematics, but this is just an easier way without having to use our kinematic equations because we know energy is conserved. Again, we're assuming there's no air resistance here and therefore no energy lost to friction with the air. Okay, so let's look at one that has a little more to it. If I cannot move it around. It says a 75 kilogram student is on skis at rest atop a 6 meter high hill. They slide down the hill, so here's where they are at the start, and they slide down the 6 meters, and then when they get to here, they coast, and it takes them 28 meters before they come to a complete stop. So it asks us, what is the magnitude of the force of friction that stopped the student? So really this problem is solving for the force of friction from here to here. Okay, so we know that, well, let's see what they give us. So force of friction is going to be this direction. We know that because it's opposite the direction of motion, and we have displacement. So that should give us some keys right here, that force and displacement, that's going to be work, right? Work is equal to force times displacement. Okay, what else do we know about work? Well, we also know that work is equal to the object's change in kinetic energy. So that would be kinetic energy final minus kinetic energy initial. So in order for me to do that, well, at the end they stop. So their final velocity here is 0 meters per second. So there is no kinetic energy at the end. So really we would say work is equal to, in this case, the opposite of its initial kinetic energy. So its initial kinetic energy is right here, right? This is where friction is slowing them down. So we want to examine this part of the problem. And so we want to know what their kinetic energy is here, because if we have that, I can take work is equal to the opposite of kinetic energy and substitute it in right here. So I'd be able to say the opposite of kinetic energy final is equal to force times displacement. And I'm looking for the force of friction. The force of friction is what's slowing them down. So algebra, get rid of that distance. Force of friction is equal to their kinetic energy. Oops, I'm sorry. This is not final. This is initial. The opposite of their initial kinetic energy divided by their distance, so 28 meters. So I have this. I need their initial kinetic energy. So when they get to the bottom of the hill, what is their kinetic energy? So, okay, keep working backwards here. I am looking for kinetic energy here. Well, potential energy here is going to be equal to 0, right? Because they have no height. They've gone down the 6 meters. So all their energy is going to be kinetic. So energy is conserved. So now let's look at this. I'm going to outline it in blue. We're really looking at this as its own problem for a moment. So we want to know however much energy, total mechanical energy it has up here, that's how much mechanical energy it has down here as well. So I would say mechanical energy initial is equal to mechanical energy final. So this is the final of this part in blue. So mechanical energy initial, it says they're at rest, so their velocity up here is 0, which means there is no kinetic energy here. So no velocity means no kinetic energy. So all of their energy must be potential. We can write this out again. Long form, kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. And so they'll have no initial kinetic energy at the top of the hill, so this is gone. And they have no potential energy at the bottom of the hill because their height is now 0. So if I can figure out how much potential energy they have at the top, I will know how much kinetic energy they have at the bottom. Potential energy at the top is mass times acceleration due to gravity times height. So that would be 75 kilograms times 9.81 meters per second squared times height, which is 6 meters. So if you do that, I get them having 4,415 joules of potential energy at the top, which means at the bottom that must also be equal to their kinetic energy at the bottom. So now I know that this student at this spot, I'll do it in red, at this spot right here, they have 4,415 joules of energy. So that's how much energy they have here. And by the end, they have no kinetic energy because they have stopped. So therefore, I just solved for this kinetic energy. So to solve for the force of friction, I would take the opposite of their kinetic energy, which is 4,415 joules, and divide it by how long it took them to stop, 28 meters. And I would end up with the force of friction. Okay, so let's stop and analyze right now. I'm going to get a negative number. Does that make sense? Well, yeah. Their displacement is to the right, and their force of friction is to the left. So if my force of friction is to the left, then I should get a negative number. So that's good. And then if I take that 4,415 divided by 28 meters, I get a negative 158 newtons. So it looks like the ground, the force of friction between the snow or ice and their skis was 158 newtons to the left, and that is the force that slows them down. So hopefully, I know there's a lot going on here. We needed to think through multiple steps, but really this problem is a good example of how we can tie together our understanding that work is equal to change in kinetic energy. Work is also equal to force times displacement, and that allows me to tie these two equations together. We did that in the last one, but now we know that an object's kinetic energy can be used or can be determined because we know that however much mechanical energy it has at the beginning, it has to have that same mechanical energy at the end. So I hope that helps, especially as you work through the practice problems. There's a couple similar to these two problems in there, but if you get stuck or need help, please let me know and I will be happy to help.